Good afternoon, everybody. I'm very happy to have you here in this room. This is our first open lecture for the Erasmus Mundus Masterclass. And this is open because it's just not open to the university, but it's open throughout our webpage to the entire world. So we have people assisting to this different corners of the world. Professor ZALEWSKI is the first invited person that we have to give this lecture here. Professor ZALEWSKI is director of the Center of UNESCO in Poland. He's chairperson of the Department of Biology at the University of UNIV. And Professor ZALEWSKI is only the person that developed the concept of ecohydrology. So I think for starting these open lectures, I can think about nobody better than him. So he's been cooperating with UNESCO for a very long time, with the FAO, with UNIV. So it's a person with very large international curriculum, and well, this presentation is very broad. I hope you for sure will enjoy it very much. And well, Professor, thank you very much for giving this opportunity to us, and I wish you a very nice lecture. Thank you very much.
Thank you very much, President Ciano. I would like to say that I'm very honored to be invited here because Professor Ciano and Dr. Alexandra Ciano is just the person who gives the new dimension to ecohydrology. Means they developed coastal ecohydrology. This very important aspect of ecohydrology as far as almost half of humanity lives in coastal zone. So that's why I'm very honored to be here, and I'm very glad to have the opportunity to share with you some of our work from the, let's say, beginning of the program to the recent developments. So, as far as we know that we're living in Anthropocene, this well-known picture is showing that human is really changing the earth. Changing the earth not only in the sense of using the fossil fuels and converting fossil fuels in energy and also emission of pollutants, but also recently we know, considering the economic crisis, that also change of geopolitical centers are one of the issues which are also disturbing the kind of clear pathways of the which already were just accepted by society and now has to be somehow modified and adjusted. And I think also this picture is showing us that we is warning that using this rate of exploitation of natural resources and without having alternative source of energy like the fossil fuel and such high level of consumption energy, we probably will have to change the pattern of our consumption and also style of living if we are not considering to come to a certain moment to the conflicting situations. So, however, I think everybody agreed what I was saying about that emission of pollutants using energy and matter per GDP is a challenge. However, this picture is showing implicitly, secondly, that also during this form of activities, we are modifying fundamental ecological cycle. Energy flow, nutrient circulation, but most important, water circulation. And in my lecture, I will try to show how and to what extent understanding how water in process of evolution and ecological succession was shaping the biota, and how to, using this understanding, we can reverse degradation of planet and get to the dynamic equilibrium between resources and society, global society needs. So one of the results of degradation, this biogeochemical cycle, is degradation of soils. And we know that society can accept that we'll not get a new type of computer, but will not accept if they do not get food, for example. And progressive degradation of soil in such scale can affect this great extent. How we can reverse the process? I think the interplay between biota, understanding biota dynamic, organic matter, dynamic or organic matter decomposition, all these three elements are somehow related. And I will show further how we can eventually try to do it. In reality, I use the case of Ethiopia, where recently on request of Ministry of Water we're developing the program. Effects of degradation of soil and water resources is, first of all, on left side we have an example. On left side is a road, a landscape which is not supplied with water. On the right side we have a landscape which is just supplied with small amount of water. The same road, just left and right. And we can see also that in the right side there's plenty of white points in the green space. There are birds. So it's showing that despite human settlements, despite intensive agricultural use, if water is in the landscape, the biodiversity also somehow can be incorporated and can maintain in the landscape. However, the intensive degradation of zone and also development of different type of, let's say, use of resources, like for example pastoral, intensification pastoral land use, is changing the nutrient pathways because big density of, let's say, grazers collecting the biomass in the catchment and becoming traditional way, twice a day drinking, is providing, let's say, roughly 70, 80, 90% of collected nutrients to the rivers, to the lakes, to the reservoirs. And obviously consequences are that there's no recirculation of phosphorus, nitrogen landscape, but permanent transfer to the aquatic system and accumulation in the reservoirs, lakes and coastal zones. So, overgrazing also generates accelerated erosion. Erosion is increased sedimentation of reservoirs, it's reducing the water reserve this way, and in consequence further eutrophication and elimination of tourism potential. This is Lake Tana in Ethiopia, which as you see has a nice potential condition, but because water quality is not used intensively. So now I think is question how to reverse all cascade of these processes which are interconnected, which I show on these pictures. And generally we can say that all things which have done in 20th century humanity is making the landscape dry, because in agricultural landscape and in the city we developed technology to send water so fast as possible to the sea. And this is an example of deforestation in the lake catchment Gumera River. And you see on the 70s when they start deforestation due to the demographic explosion, the daily evaporation was 4.8 millimeters, and 30 years later almost twice higher. So it means that fraction of precipitation which we are losing to the atmosphere was doubled, because we are just shifting from biological buffering of processes, geophysical process, toward the physical process, pure physical, which immediately make all parameters more stochastic. It means oscillating in bigger range. What is even more impressive, in some hydrological handbooks you can find only this relation. It means that deforestation is good recipe to increase water yield in the river. Yes, because if you deforest the catchment, in this moment you accelerate the flow and the amount of water is increasing. However, if we keep in mind that we double evaporation, we accelerate transfer to the river, in this moment catchment which should produce the food and provide ecosystem services, biodiversity is getting very dry in this moment. There's no enough energy to transfer this water which is increasing in the river back to the field to irrigate. The river budget will be closed, and this is not way to do it. Additionally, accelerated flow is increasing erosion. So all this process put together has to be somehow now controlled in reverse. So at that point, it's worth to think what is evolution relation between man and environment. I think at the beginning, in the geographic era of our geographic discoveries, we were thinking that nature has unlimited potential. And so we generally, the conquest of the nature was kind of general idea. However, industrial era even increased the exploitation of the nature. We just erase of the forest in some big area of continents. However, at that time, the increasing interest in biology, like Lynn knows, demonstrate that we are dealing with very interesting diversified component, or biotic component. And this consciousness of biodiversity started to be raised as a consequence. Protection of nature, this maybe not work to preserve this, was raised. Further understanding of ecological succession process means the ecosystem is dynamic, is changing and getting more mature, and also is somehow changing the patterns of fundamental processes. It was connected with increasing evidences decline of cultural and aesthetic values, and as a fact, we created fundamentals for restoration ecology. Restoration, which obviously is important in some area, but for example, we cannot restore 70% European landscape, which is agricultural land. So this is obviously it must be agricultural land. So that's why, in a certain moment, when we start to increase our consciousness, the decline of ecosystem services, it means services which determine ability to persist on the earth, it's come to regulate processes. Regulate processes toward the goal. It means using, and there's profound understanding between biota and abiotic factors, mostly hydrology, and to achieve the enhanced carrying capacity of system. Why enhanced? Because we are approaching the carrying capacity of global environment. So it's not enough only maintain given state or even declining potential, like in case of soil degradation. So an ecohydrology is system approach based on transdisciplinary science, putting together not only two disciplines along one concept, regulation concept, but also explaining how to use ecosystem processes like management tool, complementary to technologies. And obviously, the goal is enhancement ecosystem carrying capacity, water, biodiversity, resilience, ecosystem services for society, and key element is dual regulation. Dual regulation, which means that in situation like on left side on the landscape, where we modify circulation of water by deforestation, we make a, let's say, additional supply of nutrients to the landscape, and we are only half of the nutrients taking with the crop, and half of the nutrients we are still in the soil or transferred to aquatic system. We have to rather think how to put a mosaic landscape, which will be more resistant, and also we have a more closed nutrient cycle, and also important elements of the mosaic will help to recirculate the water and increase, changing the heat budget, increase the water resources retentiveness. So this is true or not. An example from Liliana spine is showing what happens as effect of overexploitation resources in upper part of catchment, and when this overexploitation of water was stopped, in 3 years ecosystem come back to this stage. This is showing the resilience of the system. So, and other word showing how water is important driving force just to regulate the biotic dynamics and biodiversity and services. How to regulate system? This question already started from famous debate in ecology from 50s about density-dependent factors. Till 80s there was still debate, and still there was many ecologists were saying that everything in ecology is density dependent, and many schools were defining the density independent, it means abiotic factor driven. But this is one of the propositions by myself and Robert Nyman, who is trying to say that both guys are right. It means because in reality exists continuum of ecosystem from those one which, like in Greenland River, are extremely abiotically regulated, there is no chance for competition predation, up to the Amazonas, where just competition predation is major driving force, and because hydrology is oscillating in very predictable pattern for 1,000 years. And obviously, many ecosystems between, and model is trying to show how it's dependent on the size of the river, stream order, and how is dependent on temperature. This was a model which was used by FAO as a framework for program habitat modification of freshwater fishery over 20 years. A second story, which is related to the soil degradation. To start to reverse soil degradation, we have to understand what is the role of water temperature. And I think that major factor, water availability, determine carbon accumulation by ecosystem. However, the type of carbon is dependent on temperature, because in boreal zone we have carbon mostly in organic matter, and biomass is not too much. In tropical zone we have mostly carbon in biomass and not too much in the dead zone. Why? Because the rate of decomposition in high temperature is 40 times faster than in boreal zone. So obviously condition when the ecosystem accumulate lots of carbon, the side 40 times faster recirculated by great opportunity for diversification of pathways, energy flow, nutrients flow, and obviously opportunities for highest biodiversity and bioproductivity. This obviously will be still dependent a little bit on geomorphology, because soil is this determinant to great extent for productivity, and in this model is assumed if similar, let's say, geomorphological potential exists. And there was the two models that were a kind of deductive. It means based on general theory, background of ecohydrology, but on every, let's say, theory also should have inductive. It means empirical background. And the idea about that system can be regulated. It means water can be, for example, regulated to regulate biota. Water can be used. Hydrology can be used to regulate biota. Was just started from this experiment in the beginning of 80s. I had the opportunity with my two colleagues, Professor Frankiewicz and Gorda Rywinska, to do research on energy flow through the fish communities along the reservoirs. And we were lucky that in 83 of the spring the water level was very low and unstable, and riparian zone was not covered. In this moment the fish were not having spawning ground access, as success of reproduction was low, 4 specimens per square meter on the cube. And as a fact, zooplankton all July, August was very high, almost 20 milligrams per liter. This is yellow, July, August. And this zooplankton very nicely controlled the phytoplankton, and despite load of phosphorus quite significant, there was no algal blooms. And another situation was 84, when in the spring the water was maintained high and stable. Fish had a good access to spawning ground, and emergence was 40 specimens per square meter, 10 times more. They completely eat zooplankton in July, August, no zooplankton, and all phosphorus was in this moment transferred to the phytoplankton pool. So we had a situation, there was no zooplankton, high algal bloom, and what is interesting, because there was no zooplankton, fishes didn't grow up. And next year there was no recruitment. What was interesting, because zooplankton was eliminated, also predator was eliminated for several years, because predators, main pike perch, need to grow to 4 centimeters to go to piscivority, need zooplankton. So there was a depletion of zooplankton, pike perch was starving, and in this moment we lost top-down control for many years. So that's why, regulating next the process, and it was tested now even 20 years after. Dr. Isidorczyk was testing last year, and she achieved reduction by 50% predicted from the model reduction of blooms. So instead of, let's say, 17 milligrams of algae, she by just regulation water was reduced to 8. Obviously, this is only supportive measure. Why? Because weak point of this is that if flood is coming, it's destroying all interaction which we build up precisely on the base quantification process. So that's why still the stream maker should not say, okay, let's forget about sewage treatment plant and other measures. We can just manipulate water level and relax. Now this is only kind of support up to the moment, giving a little bit time to do the measures and upgrade the services of society. So now we're in ecohydrology already, so that's why general key point of theory is dual regulation. It means hydrology can be used to regulate biota, biota can be used to regulate hydrology, and this is called dual regulation. Second element, harmonization. Just to regulate hydrology in basin scale in different elements of landscape, we need to harmonize with hydrotechnical infrastructure. Let's don't destroy the hydrotechnical infrastructure. Why? Because if we modify the landscape, we modify cycle, hydrotechnical infrastructure is very often very necessary to compensate. Otherwise, the stochasticity will be too high, there is no chance to regulate. Obviously, we must understand the dynamic processes and eventually this harmonize with really ecological, by basin scale performance. Last one, integration. Various types of regulation has to be put in synergistic ways to stabilize and improve water resources, ecosystem, and so on. So now I will go to the examples how we are step by step implementing these ideas. I have to underline that that's what I'm introducing. There is a results effort of the big international team. There's many aspects which were just colleagues from UNESCO program participating and developing, and obviously coastal zone ecohydrology. First paper appeared here by Alexandra Cicciaro, who first demonstrated what I theoretically was trying to predict, saying that ecohydrology always must cover from molecular to landscape scale. And first paper about the molecular aspect of ecohydrology is done by Alexandra. So now we're coming to the, I would say the ecohydrology has two phases, terrestrial phase and aquatic phase, because methodology will be different. Here we'll have a water plant soil interaction, so we have some knowledge which is from these disciplines, and aquatic processes are to a great extent depend on knowledge of hydrologists, ecologists, limnologists, and so on. However, obviously it has to be all the knowledge put it together. So what happens in the landscape? I just select few cases and I'm showing the one element. If we remember that 50% of fertilizer from here can be in water, that's obviously such a patches of land where there is no buffering zone are dramatically supplying the river for nutrients. And effect in case of Baltic Sea is seen here. The size of circle is loads from different countries. Obviously Poland is bigger country in Baltic Sea, biggest population, almost 40 millions. So in this moment we have a bigger load, and here is natural background. It means phosphorus from the leaves, branches, insects, and so on. Here is point source pollution, and this is from landscape. So now we see that if in all Europe all the attention is put to build sewage treatment plant, yes, we need them because simply pathogens elimination. Yeah? There has to be. However, it's impossible to improve the situation in coastal zones, in reservoirs, if we will not develop the systemic solution based on low-cost, high technologies, it means understanding the processes, for landscape, because this is critical. Obviously, a country like Finland, you see, the natural background is very high because population is just very few million in relation to our space. So such country have 70% of forests instead of 70% of agriculture. They don't have to worry, but it's not too much such countries in Europe. So now let's try to organize thinking, because working so long with FAO, UNESCO, I have seen in many countries that depends on specialization. Every specialist starting the action from different side. One guy from window, another guy from door. And very often leads to the wasting of resources, and any action in the scale of the basin is extremely expensive. That's why principles has to rather try like provide a certain framework for action. So First, hydrological is quantification of process is absolutely obvious for hydrologists. However, using GIS technique, work to put identify major area of non-point source pollution, point source pollution, eventually retention of water, some other size. And here is example concerning water quality. We had that in framework of a German program, identification nitrogen sources, and we see that, for example, this area of catchment has no problem with nitrogen, the impact is minimum, and we don't need to do any action. But in this dark brown, there are areas where really some measures has to be taken. What measures I will show just for a moment. Second aspect, more related to let's say, quantity. This is from Dr. Kedji, my PhD student, Dr. Kedji's former work. She evaluated the trapping capacity for phosphorus, the Pilica River floodplain about reservoirs, and possibility of increase the absorbing capacity by floodplain to reduce the impact of phosphorus to the river. This is published in Ecological Engineering for somebody who is interested. So second principle is this harmonization, different measures like denitrification, transformation in biomass, self-purification, acceleration, and biofiltration. And I will not go this time to the details. We will go to the details tomorrow during Erasmus Mundus lecture. However, I would like to underline that lots of developments has always been based on the basic science. Because as a matter of fact, some technologies which I will show right now are just started from these findings. So these findings are showing, for example, in central Poland, the major factor which determine biomass of fish and biomass of invertebrates is calcium concentration in urine. Why calcium? Because in Margalef's paper I found the information that he says that calcium is beautifully trapping the phosphorus and providing to paraphyton, and that's why atom of phosphorus is, instead of traveling long distance, is immediately supplying, so spiral is getting very short, and this is very nicely showing process. I found also such phenomenon in Massif Central in France and some other places. So, but I will show how we use for development. Another story. This is against the classic paradigm of river ecology, that river is open ecosystems, everything depends on allochthonous matter. We found that, for example, light is major determinant of the productivity and biodiversity, and intermediate complexity of ecotones stimulate highest fish biodiversity, productivity, and all cascade. In heavily shaded streams, we have a very low, which is obviously productivity is low, and beside Rhodophyta dominates, so in this case the primary productivity is not providing food for the whole chain. And in open, probably UV radiation and also exposure to predators, to birds and so on is also So this leads to the model that when we are doing renaturization of river, we make a model for lowland river, an upland. Something happens that disappeared by my English story. So we have here the diversity and biomass of fish, and here is a light, and here is a habitat type. This is refill, pool, and transition zone. And we can see eventually how to maximize in different type lowland or upland river the biodiversity in sense of light access and also to sequence of river pools to be optimized. And this is based on the PhD, another my PhD student, Dr. Małgorzata Łapińska. So we're coming to third principle, dual regulation, and obviously now is all art to put all the understanding processes in all basins to use all opportunities, especially in the so-called novel ecosystem, which are effect of secondary succession, already were modified by man, now to increase the, let's say, carrying capacity toward our goals. An example is our interesting work with producing bioenergy in river valley. That, for example, willow is considered like a kind of the bush which is loves high water level in the river valley. And obviously this was not true, because if we make a different variety in the groundwater, very high groundwater level, 20 centimeters below the surface. The growth was very poor. If 0.8 meters, you see there's sometimes even differences are 20 times bigger. So economic, so that's why, for example, if we want to produce bioenergy, the understanding of effect of groundwater level is extremely important because efficiency can be very, very highly modified. So showing another aspect, dual regulation, that you can regulate groundwater level, also your performance, productivity and economical efficiency, some activities. Now we are developing in framework Life Plus project all the experimental work in our field station and also implementation, construction in reservoir. Here is a slave reservoir, some recreation area with big houses with probably septic tanks are not perfect because you can see toxic algal blooms starting here, and phosphorus level, which is critical for toxic algal bloom, is here and measured concentration, as you see, several times exceed. And we develop system which will be biogeochemical barriers, denitrification barriers, and also plant zone, additionally maintaining still recreation capacity by putting the jetties here, so can use for boating, swimming, if obviously we succeed, and I'm sure we succeed, and there is some pilot research for developing this complex. I think, as far as I know, nobody yet was combining plant zone with biogeochemical barrier denitrification barriers, and this obviously is 10 years experimental work in our field station, which all this. Amount of water. I would say that not only in the Mediterranean zone, the water is limiting factor, and in Poland we have no problem with water in northern part, but here we have floods. And central Poland, which is most productive in sense of agriculture, is serious or significant water, significant or periodical water deficit, and that's why it's necessary to start to retain, like Algarve now, we have to build it now, and we have lots of, let's say, green protesters. However, just if we look what big reservoir of Vistula recently is doing, that's below reservoir we have increased 200 zooplankton, reduction 50% suspended matter, 16% reduction of phosphorus. Now his reservoir is old, that's why reduction of phosphorus is lower than in when he was young. Not, it was young. And BOD 40%, chlorophyll 50%. So concerning the Baltic, this reservoir obviously has one bad thing. It's disturbing continuity. And recently we're developing the system new reservoir where continuity will be maintained, because instead of fish ladder we're developing bypass system. Bypass system which is providing 8 cubic meters per second, and largest left tributary of Vistula is having 20 cubic meters. So almost half of the biggest tributary, it should be completely enough for migration. Besides, this bypass will be constructed according to model renaturization which I show. It will be very much stimulating for rheophilic fish. Additionally, we develop sedimentation zone for organic matter. I have no time to describe that we're working on the fractioning sediments for organic and mineral. And organic sediments are used for biology plantation. And additionally, we create certain connectivity channels, islands to enhance biodiversity in this. And in general, I think that if we are talking about the role of reservoir, negative or positive, is having such shape. In pristine catchment, definitely reservoir will have a high modifying many parameters. However, in highly modified catchment, with reduced land cover, it means forests and so on, whereas hydrological cycle is very much stochastic, range of oscillation is no other way to compensate, to reduce, especially in the face of climate change, the reservoirs, however, wisely designed with many functions, and especially maintaining connectivity. Now I will go to the city, because more than half of humanity lives in the city, and which is an example city which goes from industrial era to now post-industrial era. And we develop cooperation with medical university, because quality of life is health of the people, first of all. And for example, when we analyze the alpha-benzopyrene, which is highly carcinogenous distribution in the city. And next, when we analyze how green space with water is related, you can see that if it's less than 20% of green space with water, we have 4 times more alpha-benzopyrene than in area where you have at least 30%. So it's interesting, it's very good that between 30% and 70% of the covered infrastructure, it means roof, parkings, roads, still alpha-benzopyrene, so it's enough 30% to maintain around 1. And if we reduce below 20, it means immediately we're coming to the phase of the 4 times more. So, and what we can do to increase the green space in the urbanized area. This is important because, as you see, consequences of this are in green area, asthma analogy like this, and in these places where we have a very reduced green space is 3 times more asthma allergy, and in case of children and in case of the adult is practically the same. So the very serious differences and obviously the consequences of curing these people, and also the economical efficiency and so on, are economically very significant, and costs of developing green space is orders of a magnitude lower. So that's why I convinced the president of the city that, for example, such typical sedimentary ponds which should protect cascade of reservoirs, as you see, are not especially, let's say, efficient, because they were cleaned once a year, and during a year they accumulate such amount, so they were really protecting for 1 month, and other ones were periodically providing more than trapping. So we, on the basis of our work, we developed a field station, because the city has a limited space, and Spanish experience saying that we need 2% of catchment to purify stormwater, and German 1%, and still too much because land in the city is very expensive. So in this moment we were working and we reduced to 0.1. Just combining many elements, as you see. Also some from the research with calcium effect on productivity, because self-purification is nothing other than based on mineralization and absorption and productivity. So here is all sequence different stories. We have sedimentation, geofibers, biogeochemical process, and biofiltration. So this is under reconstruction, this field system from this simple sedimentary zone, and now it looks like this. Is biological phase, it didn't grow up yet. This is immediate after construction. So we have enhanced sedimentation, the special structure, and doubling the efficiency of normal sedimentation. Second phase, we have geofibers here. Next, geochemical barriers, and biological barrier and system of regeneration. It means that every constructed wetlands efficiency declining with time because colmatation of the gravel bed. And in this case we put the special system which is maintaining, in our field station, maintaining for 5 years without needs to take away, and we will see here in this prototype, I believe theoretically should be about 10 years. So, after that we developed cascade. This is cascade of reservoirs, the new reservoirs built already in the city. Also some on the newly built reservoir, the developers are building such architecture, and this is first building which is improving quality of water in the river, because all water from roofs and from parking are going from such biofiltration system by hidden under grass. So children can play, but water is going and is just purified there. And just before we have such already place, and I believe that in the city, if we have plenty such place, as you see here is bicycle walking path, so we're trying to also convey kind of friendly communication into this idea. And all idea next was developed into concept blue-green network. This is this first river where this renaturization and purification stormwater and next retention. And the idea was that this corridor, green corridor, should provide opportunity to go to big forest this way, another forest and landscape park here, so that people from this part of the city can use bicycle and and don't need to use the cars, you can walk and so on. So, and now we are identify other area. It's why, because also another medical research demonstrate that to keep the good status, especially in Europe, we need till 67, the man must 3 times a week work on heartbeat 120. In this moment is guarantee, for example, that even after heart attack, you have 0 chance to get another heart attack in just period 15 years. And person who have only once a week such activity, in 4 years, we're changing the position, I would say. Yeah? So that's why, for example, it's necessary to create conditions, because, you know, in all industrial city, in narrow streets, it's not fun to walk 3 times a week intensively. And network gives many opportunities. You look here, you have many opportunities, many in different weather conditions, different days and so on. You can use bicycle, walking and so on. Not just 3 times a week, go to the same place, to the same park, will be extremely boring, I presume. And network is giving you a big combination. So, finally also, this such retention of water is not only improving health, not only purifying the water, but also reducing hydropicking in sewage treatment plant. It means reducing seriously cost of treating the stormwater and efficiency of treating stormwater, because many treatment plants has a bypass channels, so are not really able to purify this water going to the river and reservoirs. And finally, we also have another problem, is sewage sludge in the city, because every city produces lots of sewage sludge, and there also is necessary to do something about that. And we developed technology to convert sewage sludge into bioenergy. On the beginning, this is a result showing that sludge was quite not very efficient. However, by developing some combination, we double efficiency of conversion sludge into the. Now we have 60 hectares of plantation. This is a big sewage treatment plant in Łódź, and all the green area are 60-hectare bioenergy plantation when sludge is converted into bioenergy. And on the beginning was just 1 ton from hectare. Now we came to 10 tons per hectare. We developed mathematical model to optimize the process. And this is model for decision support system. It means decision maker don't need to understand every process which has to be considered. This is hidden in the model. He has only given parameter and can play here and immediately see reaction of the system and economical efficiency. So ecohydrology has to be translated to decision makers by decision support models like this. And another story is necessary to use foresight, because river basin is big organism, and every action has to be long-term plan, and foresight is methodology, not only forecast the future, but the management, but rather creation of future, desired future. And this is methodology invented by American Corps of Engineers, and now is implemented in many, let's say, long-term strategic planning by World Bank and other sort of institution, and also this type of the, let's say, enterprise has to be equal to purpose. And obviously now is lots of interesting story which you know developed here in coastal zone by team Professor Chicharo. Another is Center Ecohydrology was just opened in Indonesia for Southeast Asia, and us really very nicely progressing with different methodology of developing of purification systems. And the Ethiopian program has many challenges. One of the interesting solutions, I think, is just when we were invited to the area where education of sustainable agriculture was done, and there was a small lake which already was impossible to use water resources because water was toxic. When we analyzed, it appeared that dioxin concentration was very high because stream coming from the village probably was transporting lots of dioxin we were not using. So we developed the system, the filtration down. Why filtration? Because 3 processes. Erosion upstream was really filling up the lake. This whole bay is filled up with sediments, already wetland was. developed here. Second, cows were providing eutrophication already, some toxic blobs starts to appear, and third process, dioxins. So it's necessary to stop these three processes, and we built a dam, which was first developed, used the biodegradable geofibers to stop erosion. And second, we built a dam to make sedimentation mineral matter, because certain fraction of dioxin is connected with mineral matter. And next, on special, because dam is built on gravel bed, so it's forcing infiltration of water to the all green area. And in this moment, the biological system is trapping more dioxin. During 1 year, we discover a reduction of dioxin 10 times in the lake because this system. And third element, what we know already about cows, we organize the drinking place on the bank. So the manure is collected here, digested, and used for fertilization to show the farmers that it's better to make an effort and put the water to drinking place, not in the stream, put the cows to the stream, because they provide very important fertilizer, and obviously this which are fertilized, plants are 3 times higher than those on it. Because in the center, 30,000 farmers was trained during the 3 years. So I think it's proper place to disseminate some solution. And during already when this was constructed, we had already postulated some other villages they won't have such things to do. Finally, we're at university, so how we have to think about teaching the people, the generation, which will be very complex. I think now universities are focusing to a great extent on providing information, understanding relations, but not enough in understanding processes and pattern knowledge. And technical university, information and overjumping the knowledge and trying to generate wisdom, ability to develop technology. So I think it's necessary in university we must make a good balance between all three components, and in technical university integrating different sciences, and that's for sure will be much more, let's say, stimulating creating the young people who are in great potential to get good job. And finally, in environmental science, now we are teaching the narrow specialist, and the same high diversified broad background, but next we have specialized. And next specialist, for example, is the same. So they are sitting in 2 towers and no way to communicate. So now probably we have to, after specialization stage, go further and try to give a chance to communicate, to understand all the specialists, and in this moment find really sustainable solutions. And obviously concerning the water, I would like to show the priorities, 5th phase, and 5th time will have a similar topic as this lecture, and let's try to answer the question. One, why in Anthropocene era we need transdisciplinary problem solving environmental science, such like hydrology, because we have to reverse process of getting dry, polluted and nutrient depleted. And because in the world which is approaching carrying capacity, relation between society, water, environment become highly complex and might lead to the conflicts. And that is why we need such transdisciplinary science background for reversing degradation and enhancing carrying capacity. I think always we have to answer the question if we want to live in such techno garden or in garden, but I think our students should create something between. Thank you for your attention.
Professor, for this brilliant lecture. I want to thank everybody for your attention, and also people that were assisting through the web. We will continue this kind of lectures further on. For now, if you have any question, Professor, please. It was very interesting because it allowed to show that because it is applied in different regions for different aspects, from the urban to the coastal, from the molecular to the biodiversity aspect, so from the entire catchment area. So I think it's a very broad science. Also that it's transdisciplinary, so it links with different aspects and different sciences that we need to put together. And so this is a brilliant theory that we need to develop in terms of solving problems for future. I have one question for you, is that we are in this process of climate change, and everybody is talking about that. And Ecohydrology deals with water and deals with biota. But hydrological cycle will change, of course, due to climate change. So my question is, if can Ecohydrology be a sustainable solution even in terms of the changes that are expected, predicted for climate change?
Yes, I already this morning said that glass is always half empty or half full. It means climate change is giving some opportunities, like acceleration of mineralization process, which is key self-purification of river. But on the other hand, and that's also absorbing capacity of plants is increasing, so we can more efficiently use phytotechnologies for let's say some purification system. But on the other hand, is putting more stress on water budget, and more carefully we have to somehow regulate. Now, for example, in Ethiopia, when we calculate the budget in the Rift Valley lakes, which are drying, we just found that they just declined 1–2% of the water budget a year. It means it's a rising decline, but the reverse process is enough to put the shelter belts of tree, which will reduce speed wind and in this moment rate of evaporation, just every 400 meters, theoretically. This model has to be tested now empirically. However, it's showing that in this moment we change about 4% of water budget positive way by reducing wind speed. And in this moment we can probably reverse the process of drying the lake. However, still lots of research is needed in different parts of the world on such process, such solutions, and that's why I think our students here will just take a challenge and will do it. And develop, and many other more brilliant even ideas.
Is there any question?
Yes, I've got a question. What is the approach for eco-hydrology application for those cities in third world countries where the population is quite high and there is no space to build up something like dams that you have shown in huge? So what would be the approach or the perspective to apply or implement all these eco-hydrological solutions for those problems?
Yeah, I think always if you look on some space, means you have to always look for the basin. In basin always you will find the ability to, some measures, which already examples. So I'm saying that unfortunately river basin is superorganism. Each is different. Like another antibiotic will be good for me, another for you. And the same, that's why, still I think that it's necessary to, that's why it's so important is understanding general theory of ecohydrology, because having an understanding general theory, you can adjust to local condition solution, because hierarchy of drivers is different, hierarchy of problems is different in every basin. And that's why ecohydrology is not just cookbook recipe that you can select this or this recipe and solve the problem. You must put your integrative transdisciplinary knowledge and try to, obviously you can support yourself by analogy with some solution, but it needs, some kind of really creative thinking, and I think it's best insurance for an employment for you.
In general, we have rich countries and poor countries, and essentially the rich countries do all the research and try to transfer the technology from the rich countries to the poor countries. Right? So, what do you think is the role of ecohydrology in this old model? Because ecohydrology can allow poor countries to develop new solutions, but in which extent?
Okay, in my lecture I show this system, which is a low energy system to purifying stormwater in the city. And in this moment, there's many solutions like this. I had no time to introduce in other lectures with denitrification area and so on. And in general, a synonym of ecohydrology in UNESCO terminology is low cost, high technology. Because it is low energy, low cost and high tech, because high advanced knowledge has to be use to construct this and adjust to the local conditions. And that's why I think it's especially important for countries which are not really very, let's say, rich. However, and additionally, as I today know, only half of the success is technology. Second half is systemic solutions which are just based on your understanding of system function.
Okay. So again, thank you very much for your time and the lecture, and thank you very much everybody for coming to the system. See you all.